All right, good afternoon, everyone, since it is afternoon now. You may notice that the title of my talk has changed somewhat from what's listed on the schedule. I was originally going to talk a little bit more about the standard dynamical scenarios for white dwarf pollution, but I had a change of heart at the 11th hour, decided to tell you about something that's been puzzling me a little bit more lately, and what I've been working on with my advisor, Dong Lai at Cornell. Thanks to Yi and Mark's talks earlier, I don't have to spend a lot of time introducing the idea of white dwarf pollution. I just want to remind you that the salient features that we see, for the most part, in the chemical abundances tell us that the bodies that are producing white dwarf pollution, the parent bodies, tend to be rocky in composition. You see a lot of refractory elements, your oxygen, silicon, magnesium, and iron, and very little, or at least a few systems that show a lot of volatile elements, things like carbon, nitrogen, and sulfur. And this generally can be interpreted in terms of what types of bodies are being accreted by white dwarfs. Rocky bodies will probably be more like asteroids in the solar system, or maybe fragments of terrestrial planets. Whereas the icy bodies that we are, for the most part, not seeing, with some notable exceptions, would probably be more like Kuiper belt objects and, for the focus of my talk, comets. And so what I'm going to try to convince you of is that the lack, or at least rarity, of icy parent bodies should really be puzzling us, and it might actually be indirectly telling us something about the planetary systems in which pollution is occurring. So to motivate the idea that we should even be seeing comets in the first place, I'm going to appeal to the fact that we know exocomets are out there. In particular, we know they're out there around the progenitors of most of the polluted white dwarfs we see, because there are plenty of observations of early type main sequence stars, A and F type stars mainly, that show the signatures of exocomets. The most famous instance of this is in the Beta Pictoris system, where you have time variable spectroscopic absorption features that are attributed to so-called falling evaporated bodies. But there is also now a growing number of systems where Kepler and TESS have shown asymmetric transits, like this example from a study by Saul Rappaport and co-authors, that seem to be the tails of comets passing in front of the host star. And so really, it's hard in this context to imagine why we shouldn't be seeing exocomets around the white dwarfs that will result from these systems if we see them around the progenitors. Now, this all has to take place in the context of some model for the delivery of those comets by dynamical means. And what I'm going to use as a standard picture is the picture we have for the origin of long period comets in our own solar system. Now, the standard theory that dates back to even to the 50s is that they come from the Oort cloud, which is this extended swarm of something like 100 billion kilometer-sized objects that extends all the way out to close to a parsec from the sun, so really the very limits of its gravitational influence. And these comets only are observable when they get tweaked by some sort of gravitational disturbance, so that they fall all the way in and develop a tail due to irradiation, become observable to us. And the reason I think that this might be a good model for comets is that the Oort cloud is associated, at least in our solar system, with the evolution of the giant planets. These bodies were ultimately ejected from the planetary zone at some point in the past. Now, to give a little bit more into the details of how this occurs, this comet delivery occurs, that is, what you have is, at the very, very center, close to radius 0 by comparison, you have the sun and its planets. Out here you have the Oort cloud, and this all exists within the context of the galactic disk. What happens is that the galactic disk exerts tidal forces on the Oort cloud, again, because it's at a parsec scale, so the gravitational field of the galaxy is important. And that tidal force can sometimes rob a comet of most of its angular momentum, so that it will fall inward, come close to the sun, and be observable in the usual way. And in fact, there exists a very nice analytical formalism for understanding the rate at which this occurs. This is due to Heisler and Tremaine back in the mid-80s. And you can use this formalism as just a sanity check of our scenario to more or less reproduce the rate at which long-period comets enter the solar system for the first time as observed in our solar system. So this heat map shows over a range of different density profiles and radial scales for the Oort cloud in our own solar system, the amount of comets that come in per unit time. And there's a handful of dynamically new comets every year, even though most of them don't become bright and visible to the naked eye. So this gives some reasonable confidence in the scenario I'm selling. Well, you can do the same thing for a white dwarf endowed with a solar system like Oort cloud. There's nothing really special about coming into an AU-like distance. You can probably, if there's nothing to impede you, fall all the way to the Roche limit and be disrupted. And so under that hypothesis, you can calculate that the time averaged accretion rate, the delivery rate of metals from these comets, will be across the same range of comet Oort cloud models of the order of magnitude of 10 to the 8 grams per second. And that's right in the middle of the distribution of accretion rates you see, at least at very long ages where things like extra mixing processes probably aren't relevant. And so I claim that under this naive scenario, we should be seeing a comparable amount of volatile-rich pollution in the polluted white dwarf sample to rocky, bulk Earth-like material. And this is what I really mean when I say that it puzzles me that we don't actually see too much of that. Now, I sort of did a little bit of sleight of hand here because we shouldn't necessarily think that the Oort cloud around a white dwarf will look exactly like the Oort cloud in the solar system, because some things have happened in the meantime. In particular, the star has evolved through a post-main sequence stage, and for various reasons, that can lead very efficiently to ejection of comets. So the first thing we should do is get an idea of how much that's going to deplete the Oort cloud and reduce the rate of accretion. So the two major processes that deplete an Oort cloud on the post-main sequence are first just isotropic mass loss from the star by conservation of angular momentum. As your central mass diminishes, your orbit will tend to grow. And if those of you who are familiar with supernovae know that if you're far enough, that the mass loss happens over a short amount of time in terms of orbital period, then you're going to just be impulsively ejected. And indeed, one possibility for depleting the Oort cloud, and various other people have looked at this. This isn't originally my idea. The other possibility is that you have a natal kick imparted to the white dwarf. This will tend to make matters worse because in addition to the expansion, your center of mass will start running away due to asymmetric mass loss. And there seems to be a reasonable body of evidence that white dwarfs receive a natal kick that is in fact comparable in magnitude to the escape velocity in the Oort cloud. So these seem like good candidates for how to knock down the numbers somewhat. Well, it's pretty easy to use some standard n-body software to examine this, with a simplified mass loss model, a prescription for how the kick gets applied during mass loss, thank you. You can get that over the typical range of white dwarf kick speeds inferred by Karim El-Badri in a recent study, you lose, on average, probably around 90% of the initial comet population that you had. Okay, you lose a factor of 10 in accretion rate, all else being equal, but 10 to the 7 grams per second is still pretty close to the middle of the distribution of accretion rates because there's a lot of spread. So it doesn't seem to me that post-main sequence dynamical evolution is enough on its own to explain the absence of white dwarf pollution, at least in most systems. Maybe it reduces the fraction somewhat, but we should still be seeing a little bit more of it, I claim. So that tells me that there's something else going on, and what I want to be true is that maybe it's telling us something about the planetary systems. We know, again, from the example of the solar system, that long-period comets are moving close to escape velocity. They have parabolic orbits. And so at perihelion, they're very, very vulnerable to even small kicks in the velocity imparted by a planet, such that they can be excited then onto a hyperbolic orbit and not return again. And so a nice way to understand this is just that if you get a random energy kick, either up or down, you're going to be very vulnerable to being ejected. You'll be ejected about 50% of the time if the size of that kick is characteristically greater than your orbital binding energy. And that gives a nice scaling with the mass and separation of the planet. Now this calls for more n-body experiments. And you find that, indeed, you can create, as we see in the solar system, a pretty strong barrier, a pretty strong reduction of the amount of comets inside the planet's orbit if the planet is sufficiently massive. So we really see a strong barrier effect kicking in. This shows ejection probability with respect to pericentric distance, you see this kicking in at a characteristic mass ratio of around 10 to the minus 3, so pretty similar to the Sun-Jupiter. Thank you. And remembering the fact that this doesn't happen over one orbit, that a comet falls all the way to the white dwarf. It takes many, many orbits for the weak perturbation of the galaxy to actually bring you all the way down to the Roche limit from something like a few AU. And so I claim, although it's a little bit harder to justify this quantitatively without doing some more complicated statistical calculations, that you will have a high ejection probability over successive passages of the comet. And so with a strong enough barrier effect from a planet, most of the comets will be ejected before reaching the tidal radius. And you can just imagine there's some sort of fudge factor that comes out of the more complicated statistics to reduce the accretion rate. So now let's put these together. If you assume that there's a fraction of the comets that survive into the post-main sequence to begin with, there's a depletion factor as a result of there perhaps being a planetary system, and then an additional fudge factor based on the fact that there might not be perfect efficiency of tidally disrupted mass being accreted by the white dwarf, you can indeed knock down the accretion rate relative to that naive Oort cloud delivery value down to by about 3 orders of magnitude. And from 10 to the 8 grams per second, that gets you down to 10 to the 5, which is comparable to the detection limit quoted in a lot of papers I've seen. And also just small enough that even if maybe it is above the detection threshold, we already know we're seeing rocky pollution at a characteristic order of magnitude of 10 to the 7, 10 to the 8 grams per second. So you could still overwhelm the comet signal just with other pollution, perhaps. Again, this is with the caveat that it's difficult to estimate that barrier factor rigorously, but this certainly gives an idea of what might be necessary. So I conclude that the following is a possible, not necessarily a unique explanation for why we might not be seeing comets accreting onto white dwarfs. You have to receive a natal kick. We have good evidence that that seems to be happening in a lot of white dwarfs. And you will have to have a surviving planet, not just of any mass, but with a mass ratio typical of giant planets and a radial scale typical of giant planets as well. So this really seems to be a hint that when we finally become able to detect planets at ice line-like distances from white dwarfs, we really should expect to see something more like a Jupiter, if this is the right explanation for why the comets aren't showing up. There's the other more interesting possibility, or equally interesting possibility, I should say, that something is preventing Oort cloud formation around A to F type stars. That's really beyond the scope of this work. And I hope to put a paper out about this reasonably soon. So thank you for your attention. Let's have some questions and then go to lunch.
Questions? Yeah.
Hi, Chris. Very nice talk as always. I was wondering about what you say about the galactic tide. You know, like the rate for the comets that come into the solar system, well, to the planetary system itself. Because the galactic tide in general, it just helps to form the Oort cloud, to circularize the orbits in the outer edge. When you do like a longer integrations or like the planetary system is evolving even in any stage, the galactic tide is barely doing something. It's just like the edge of the Oort cloud. Like, so what it actually does, the comet shower like thing is stars around. You know, like in the environment, that's what matters the most to create comet showers. So I was wondering if maybe it will be a nice exercise, or you already did that, to include some environment of this white dwarf or planetary system that you have, and kind of compare whether you can have more or expect more comets coming into in the inner planetary system.
Yeah, so that's a great question. Thank you, Santiago. So my understanding was that, at least, you know, maybe this is a problem with reading papers from the 80s, maybe the story has changed somewhat, was that the galactic tide tends to dominate because of the ratio of the total dynamical density being dominated by dark matter and gas versus the stellar flybys, which are a much lower effective mass density. But maybe that's been updated somewhat. I have done a little exercise to figure out what the duty cycle of comet showers are. And that tends to be less than about 10%. So maybe that could explain a little bit as well if, you know, if in addition to the galactic tide, there are stellar flybys. The probability of catching a white dwarf in the middle of a comet shower is relatively low.
Yeah, just a small comment. Yeah, at the beginning, when all the R cloud thing was like more hot, very long time ago, yeah, that was the idea, that the galactic tide, you know, was the kind of the stronger thing. There is a lot of papers out like with a more sophisticated simulation that show, like, yeah, of course, it does have a good effect, but the stellar flybys make a more impact. But well, we can talk about it.
Yeah, it's good to know. I mean, I will say that, again, that it being the galactic tide is not as important as it being diffusive. As long as it takes many cycles to diffuse all the way down to the Roche limit, then the planetary barrier effect should still at least be important.
Hi, Chris. I was wondering, so this is probably a question not just for you, but for everyone in the metal pollution community. Is a lot of your effort has been trying to bring down the expected accretion rates of these comets, but are we sure we're not biased against detecting these metals, these elements, particularly in the optical? And the vast majority of metal pollution, we've only detected in the optical. And as C said, we then go to the UV to make sure we characterize this properly. Stuff like carbon, are we biased against seeing these? So maybe the rate is higher than what we are actually seeing?
So I had the exact same question, and I asked Boris and CE what they thought about it, so I will defer to them.
So yeah, the answer is that there's enough unpublished ultraviolet cost spectra that various people have collected that there aren't large numbers of carbon detections or nitrogen. So I think nitrogen is the best tracer of comets. And it's a bit harder, but I think, I don't know what C says.
Yeah, I agree. And then I think another thing is there is carbon, if it's really carbon heavy, like there can be carbon detection in the optical. And I think TON 345, like it's so carbon rich relatively. So we do have carbon detection in the optical. So yeah, I agree.
But those carbon abundances are still very subsolar, is that right? Okay, thank you.
So, Harvey Richard, natal kicks are a good idea because I don't know what motivates them. Probably a deficiency of white dwarfs in open clusters, I think, is one of the things that motivates them. But do you have a physical mechanism for the kick? I mean, people say, well, asymmetric mass loss, but is there something cleverer in that? Or
I do not. The best I've done is just assume that there's some dipole asymmetry in the wind and have done with it. I know that there are some constraints on the expansion rates of planetary nebulae in different directions, and that show that the wind has to be, I think, isotropic at least within something like at least 10% by mass, but I think you only need percent level asymmetries to generate kilometer per second kicks. I could be wrong though, it's not really my expertise. I just included it sort of phenomenologically.
Jim?
Thanks, Chris. So our solar system has a planet with this mass at those semi-major axes.
Mm-hmm.
What are the thoughts about whether or not Jupiter shields our solar system from comets coming in all the way in? And
I think people definitely think it does. The actual dynamics of comet delivery is more complicated than the simplified picture I showed because there's more than one planet, so you can have comets sort of jumping around in semi-major axis due to repeated scatterings rather than being ejected. But certainly if you apply the Hessler and Tremaine formalism to get the rate of sun-grazing comets, you get something about an order of magnitude higher than what you observe. So I think that's a plausible justification for this, although it's not perfect.
Quick question.
Ava seems to have one.
Hi. Have you considered the fact that the comets turn into asteroids when you have a hot enough star?
I have thought about that a little bit, although I'm not convinced that that's hugely relevant. The reason being that the orbital period in the Oort cloud is about 1 million years, which is roughly the duration at which the star is extremely luminous enough that you would probably start to outgas. So you might have that happen if you get unlucky enough to plunge through pericenter from the Oort cloud and pass close to the AGB star, that you get devolatilized. But I don't see it happening for a huge fraction of the cloud. It's plausible though. I'd have to think about it a little bit more carefully, and maybe we should talk about that.
Quick one.
So when comets get scattered from the Oort cloud, what is their typical semi-major axis? And have you thought about what the accretion timescale would be for such extremely long semi-major axes? I'm hinting at the idea that perhaps the accretion timescale is sufficiently long that you wouldn't actually accrete the material into the white dwarf.
Yeah, that is an interesting suggestion. I suppose that was along the lines that I put in a fudge factor just for the accretion efficiency. The orbital period, as I said, is about 1 million years. So if you have a very long debris stream, then yes, it may get spread out. But at the same time, you expect to be disrupting a comet every few years. So in steady state, I think you would still expect to see the same amount of metals going in overall.
It's lunchtime, so we can continue discussions at lunch. Sorry, JJ. Thanks to our speakers in the morning. Please be back at 10 to 2.